Session, we have three short presentations. As I indicated in the morning, I presented a high-level overview of a lot of new designs we are working on. So in these short presentations today and tomorrow, we'll be able to give you some more details on those designs and the performance numbers. So today's we have like three 10 minutes presentations by three members of the MAPIS team. So the first one will be presented by Mamji Byadpur. He's a PhD candidate in the CSC department. He received his PhD degrees in computer engineering from the Sharif University of Technology in Tehran, Iran. And he has been in the group working on the MAPIS project since 2015. His research interests include high-performance computing and parallel computer architecture. He has authored or co-authored over 15 papers in the conference and journals related to these research areas. So he has been working actively on the hardware tag matching and also the SAR, which the numbers are indicated in the morning. So in this presentation, he will go more details into the hardware tag matching in MAPIS 2X. Let me also introduce the other two speakers, so that will help us cutting down the context switching overhead. So the next talk, short presentation, will be presented by Mahadieh, Ghazimirsaeed. She graduated from Queen's University, Canada in March 2019. And after that, she has been a postdoctoral researcher in the CSC department at the Ohio State University. So she is also actively involved in the MAPIS project. Her research interests are high performance computing system, heterogeneous and accelerated computing and cloud computing. And she has done this work on this neighborhood collectives. I presented some initial numbers. She will go into more details on efficient support of large message neighborhood collectives in MAPIS 2X. The final talk of the session will be presented by Arpan Jain. He is a third-year PhD student. He received his bachelor and master's degrees in information technology from ABB IITM India. So currently, he is involved in the HiDL project, the high performance deep learning project, and also actively contributing to the MAPIS 2 project. So his research interest lies in the intersection of the HPC and deep learning and parallelization and distributed strategies for large scale DNA training. And in the today's morning keynote talk, Brian also indicated some of his work he had done during his summer internship. This just last summer, just he finished this internship. So he will be focusing more on the accelerating the CPU-based training. I introduced that in the morning through the robot stack. We are able to integrate to our MAPIS 2X and MAPIS 2 GBR. So with this introduction, so I think Samir has come back. Samir, sorry,
yes.
we lost you for some time. So I went ahead and introduced the next speaker, but we can take the QA. We can do dynamic scheduling. Okay.
Okay, thank you. I'm sorry, my laptop just died at the last slide, but I would be happy to take any questions that you have either now or I can also take it on Slack.
No. There is a question. We can take it now. There is a question on the QA box. Please take a look.
So Dr. Panda, like he will not be able to see the question. Can you read it out for him?
Oh, okay. So this question is source instrumentation of C++ 11, 14, or 17 code supported by Tau via PDT?
Via PDT, our parsers do support the Edison Design Group EDG parsers for source instrumentation. Now, there may be some features of C++ that are better supported by the compiler-based instrumentation. And we are also working with LLVM compilers, and we have a new plugin that we'll be releasing soon that allows you to do selective instrumentation with LLVM-based compilers. So you can just target the instrumentation in specific code regions and not incur the overhead of instrumenting every single constructor, destructor, and trivial function. So we support compiler-based instrumentation. PDT is also supporting source instrumentation, but it may lag behind the standard. It may support, like, for example, C++ 14 well, but not 17. And with a moving standard, that's always a risk. But I would suggest that you start with event-based sampling, and then you can have the minimal overhead and then move on to more targeted instrumentation based on that.
And I just want to add one, or you might comment. I mean, whatever you proposed, like directly people can download Tau and MHAPIS2 and it will work.
Yes,
Yeah, so.
it will. Thank you.
Are there any other questions? No.
If not, I'll just monitor the Slack channel.
Yes, please, if there are any other questions, please follow up on the Slack channel and Samir will be very happy to answer those.
Thank you.
So with this, let's switch to Mamji, if you can share your slides and start presenting.
Yeah, sure. Can you see my slides?
Yes, yes, it is there. Yeah. Please go
Hi,
ahead.
everyone. I'm Mamji. Thank you, Dr. Panda, for reading my bio. And today, I'm following up on the discussions that we had on Harvard tag matching, which Gilad mentioned, as well as Dr. Panda and some other speakers. Today, we will have a quick overview of our efforts for the Harvard tag matching in MHAPIS2. So HPC applications require high performance, low overhead data paths that provide multiple things. For example, they need to have low latency, high bandwidth, and high message rate, as well as they should provide good overlap of communication and computation inside the application. So in order to meet all of these bullet points, modern InfiniBand clusters they have provided these new features inside the HCA, which is called hardware offload tag matching. So basically, we want to see in this project, how can we take advantage of this tag matching offload inside Connect X6 and provide the support inside MPI and see how does it perform at the application level. So hardware tag matching offloads the processing of the MPI point-to-point operations from the CPU to the HCA. So we have two most common protocols for point-to-point operations. So one is the eager protocol, which is usually used for smaller messages and medium messages. So using hardware tag matching, we can provide a completely zero copy transfer. Basically, there is no copy in this eager protocol, which can be useful for the medium messages. Also for the rendezvous protocol, the processing of the handshakes can be offloaded to the HCA. So we have done all of our experiments on the Frontera, which has like around 8,000 compute nodes, and it has a Cascade Lake processors. It also supports Connect X6 HCAs, which has the hardware tag matching support. And in the following experiments, we are comparing the impact of hardware tag matching on the performance of MHAPIS2 X2.3 RC2. So let's start from the point-to-point operations. So here we are showing both eager as well as rendezvous protocol, and we ran OSU latency, which is a completely communication benchmark. So it doesn't have any compute. So here we want to look at the pure communication. As you can see that for the eager protocol, especially at the medium message ranges, where the copy overhead can be having impact on the total latency, we can see up to 35% benefit at the OSU latency level. But on the other hand, for the rendezvous protocol, since there is no copy operations, even in the CPU-based rendezvous, there is no change between whether you have the hardware tag matching or not. So here it shows that the benefits of hardware tag matching for the rendezvous range usually comes from the impact of the overlap, which we will see in the next slide. So here I'm showing the impact of the overlap. So we ran OSU iScatter to look at the performance of MPI iScatter. So we ran from 128 nodes to around 1,000 nodes on Frontera. And as you can see, because we are having the overlap of communication and computation, which can be crucial, especially for large messages, we can gain up to like 1.8x benefit in total latency which this benchmark reports. So if we go ahead and look at the IL to all, we see a similar trend here. It's around like 1.8x benefit. So this benchmark, OSU IS Gallery, also reports overlap of communication and computation inside the benchmark for various message sizes. So here we can see that like how does the performance overlap is actually looking like. So you can see that if you have hardware tag matching enabled, you would see that the overlap is around like 100%. So as the application is performing the computation and it is not inside the MPI, HCA can simultaneously take care of all the necessary handshakes of the rendezvous. So it can provide like around like 100% overlap for large messages, which is reflected in the previous slides where we are seeing the overall latency. Similar thing is also happening for the MPI IR as well. So you would see around like 100%, especially for larger messages after like 128K. And if you want to look at the application level benefits of the hardware tag matching, we have evaluated these benchmarks: 3D stencil, PTD, FFT, LAMMPS, and NECPON. And you would see that you can see like around like from 4% up to like around 32% benefit at the application level. And here I'm detailing the like scale. Like for example, 3D stencil has been run on 128 nodes with 56 ppm. ppm means like processes per node, and this is the unit that I'm measuring. So this is the overall runtime. So the benefits that we are seeing, this improvements, it's on the top of overall runtime for the 3D stencil. And also for P3D FFT, this is the time per forward, backward, forward FFT loop, and it's around like 8%, and the rest is also mentioned here, which is mostly execution time and the computational speed. So with this, I want to conclude our quick overview of the hardware tag matching. So we have proposed efficient designs for hardware tag matching inside the MPI, so that applications can take advantage of this feature. Also, we have seen benefits of the hardware tag matching inside the MPI up to like 1,000 nodes on non-blocking collectives, and this feature will be available in future MVAP2 release. I will be happy if I hear some questions. Thank you for listening to my talk.
Yeah, Mamji, there is a question on the QA box. Please take a look.
Yeah, let me see.
I can read the question out. So, Mamji, the question from Sayantan is this: is the iScatterV benchmark doing any overlap, or is it part of OSU benchmarks?
So iScatterV, to measure the iScatterV, we are basically using OSU micro benchmark. So in OSU micro benchmark, we have some dummy compute. So basically we call MPI iScatterV. Then after that, we have some dummy compute. Then at the end, we will measure the overall runtime. So that's how we are measuring the overlap as well as overall runtime.
Okay.
But these are all included inside the OSU micro benchmark. So we didn't change anything inside the benchmark. We just ran OSU underline iScatterV.
Okay, thanks.
The system is Frontera.
Can you repeat the question, please?
So Gilad is asking what were the systems used for the application benchmark. So we use the Frontera.
The Frontera system at TAC.
Yeah, all of our numbers are from Frontera. Is there any other question on Slack or?
No.
I think, I think that's it. Thank you.
Okay, so Mamji, thanks. If there are any other questions, please follow up on the Slack.
Yeah, sure.
So Mahdieh, you can share your slides and then present.
Can you see it?
Yes.
Okay, hello everyone, and thanks Dr. Kanda for the introduction. So I'm going to talk about efficient support for large message neighborhood collectives in MVAPISH 2X. So what is neighborhood collective, and how is it different from ordinary collectives? So in ordinary collectives, all the processes in the communicator communicate with each other. But in neighborhood collectives, the processes only communicate with their incoming neighbors and their outgoing neighbors. So what is its benefit? First of all, the user can define the communication pattern, and more importantly, it has better scalability. But unfortunately, the MPI implementations are not using neighborhood collectives because it is a relatively new concept in MPI. So the question is, how can we design non-trivial algorithms to optimize neighborhood collectives? So first of all, we need a fully distributed algorithm, and we assume that we don't have prior knowledge about the communication pattern of the applications. In this talk, I'm going to talk about large messages, and we are trying to reduce the number of inter-node communications. And in neighborhood collectives, there are two phases. First of all, we need to create the communication pattern, and then based on the communication pattern, the processes communicate with each other. So assume that in this figure, process 0 wants to send the data to process 5 and 6. So the naive solution is that process 0 just sends the data to these processes. But if we want to consider the hierarchy of the system, it would be better if process 0 scatter the data between process 5 and 6, and then process 5 and 6 do an intranode altogether. So here you can see the graph comparing the hierarchical design with direct approach. And as you can see, with the hierarchical design, we can gain a lot better performance. So when the application is running, the processes might participate in a lot of communications. For example, in this figure, process 6 is receiving a lot of data from a lot of processes in node 2. So one question that arises is that, so when process 0 is scattering the data between process 5 and 6, how it's going to distribute the data between these processes? So the naive solution is that it just divides up the data between these two processes, but it's not a good approach because process 6 is very busy with other communications. So it will be more fair to assign less amount of data to process 6 and more data to process 5. And here you can see the results with the load-aware approach and the load-agnostic approach. And as you can see, when we consider the communication load of the processes, we can significantly improve the performance. So the question is, how can we redesign neighborhood collectives to take advantage of the hierarchy of the system? The second question is, how can we consider the communication load of the processes to fairly distribute the load between them? And the other question or challenge is that the MPI applications are not using neighborhood collectives because, as I said, it's a relatively new concept in MPI. So how can we redesign MPI applications to take the many benefits of neighborhood collectives? So we propose two design alternatives. The first one is called load agnostic hierarchical design. So in this approach, we have 3 levels of communications, and we try to reduce the number of inter-node communications. The other approach is called load-aware hierarchical design, in which we derive a mathematical model to define the capacity of each process, and then based on that, we assign fair amount of load to the processes. And we run our experiments on 2 clusters, Frontera from TAC and Comet from Exceed, and we added our results to MVAPISH 2. So here you can see the numbers for more micro benchmark on up to 28K processes. And here we show the benefit of load agnostic hierarchical design compared to the direct design and in MVAPISH. And as you can see, we can gain up to 9x speed up with this design on up to 28K processes. So one question that might come is that why we are not comparing it with load-aware hierarchical design. So the reason for this is that we observe the same performance with load-aware hierarchical design. And the reason for this is that more microbenchmarks has a structured communication pattern, meaning that the number of incoming and outgoing neighbors for all the processes is the same. So it is already low level. So we couldn't gain further benefit with the low level approach for this microbenchmark. And here you can see the numbers for random sparse graph for different densities. And we show the numbers for low level, load agnostic, and the direct approach in MFH2. And as you can see, we could gain up to 10x speed up on random sparse graph. And another observation from this figure is that the load ever design performs better or equal than the load agnostic approach based on the communication pattern in random sparse graph. And here you can see the numbers for sparse matrix multiplication on the left-hand side. So the SPMM code was natively written in using point-to-point communication. So we changed it to use neighborhood collectives. And here I showed the numbers with the performance gain with point-to-point load agnostic approach and load approach compared to the direct approach in MFH2. And as you can see, for different matrices from sparse matrix collection, we could gain up to 34x speed up. And on the right-hand side, you can see the performance gain for NAS. We run it on up to 1K processes. For SPMM, we ran it on up to 28K processes. So for NAS, we could gain up to 15% improvement. And as you can see in both these figures, load level approach is performing better than load agnostic approach, and both of them are performing better than the default point-to-point approach. So this paper has been accepted to SC 2020 and is going to be presented there in more detail. So to conclude, we bring up some novel designs to efficiently increase the performance of large message neighborhood collectives. We have two design alternatives. So the first one is a hierarchical design, which considers the hierarchy of the system to reduce the number of internode communications. And the second one is the load level approach, which tries to fairly distribute the load between the processes. And we showed that we can gain up to 9x speed up for more and G4x speed up for sparse matrix multiplication on up to 28K processes. This design will be available in the next MFH2X release. Thank you for listening, and if you have any question, I will be happy to answer.
Any questions? So Mahdieh, I have a small question. So selecting any of the load-aware algorithms, is there any other penalty? Do we put it at any place? Is it in the initialization time or somewhere else?
There are, because as I said, for the load-aware design, we derived a mathematical model to have the capacity of the communication for each process. So that mathematical model has a very small overhead, but it's very negligible compared to the performance gain that we have. And we showed the overhead in the paper, and we discussed it in detail. But I didn't bring it up here. But yeah, there is a very small overhead, but it's negligible.
There is another question in the QA box. Please check, and you can read that out. And
neighboring in logic or physical topology? Actually, this neighboring is in logic. It means that two processes are neighbors if they are going to communicate with each other. So for example, process 0 is going to send the data to process 1 and 6. So it means that process 1 and 6 is neighbor of process 0.
Thank you. So I don't see any other questions on the Slack or Q&A. So thanks for your presentation.
No worries.
So we can switch to the last one. Arpan, please share your slides and you can start your presentation.
Hello, Dr. Panda. Just a minute. I can't find my point. One second. So, okay. So can you see my screen?
Yes, yes, yes.
Yeah. So thank you, Dr. Panda, for the kind introduction. So I just realized that I'm the last speaker. So basically the lucky last speaker. The advantage of being the last speaker is that everybody wants you to stop talking. So let me promise you, I will be very brief, and it will be a very brief presentation. So today I'm going to talk about accelerating the CPU-based training for very large deep neural networks using the MUG'20 library. So just to refresh your memory, deep learning is a subset of machine learning, which in turn is a subset of artificial intelligence. So the key difference between the machine learning and the deep learning is the feature extraction, like how you extract the features. In deep learning, it automatically does it for you, while in the machine learning, you have to do it by yourself. So I don't have to comment on the popularity of deep learning, as it is evident by the fact that the first talk of today's program was on deep learning, and the last talk is also on the deep learning. So now the resurgence of the deep learning is mainly because of the availability of the compute power. So since 2013, the deep learning researchers are using the GPUs to train their models, and it has become the common belief that deep learning CPUs are like 10x or 20x slower than the GPUs. However, this is not the fact. The CPUs are also getting faster for the deep learning, and with every new architecture, we are seeing better performance for the CPU. On the architecture side, we have many core Xeon CPUs, Power 9, and the EPIC architecture. And since architecture is not enough alone, so we need softwares also to get a better performance. So that's why we have MKLDNN, which is a math kernel library by the Intel, and vectorization and optimized MPI libraries like MUG'2, so that we can scale the distributed deep learning using on the CPUs. So, and also the CPU only systems are emerging, like Frontera, which is a CPU only system, and it has 8008 nodes, compute nodes, and it has a Intel Cascade Lake processor. So that's why we present MUG'2 driven infrastructure for the MLDL training, where on the top you have the ML or DL application, and you can use any of the popular deep learning framework like TensorFlow, PyTorch, or MXNet to define your model. And to run the distributed training, we can use the Horoword high-level distributed deep learning framework that can be configured with MUG'2 GDR or MUG'2X, depending upon where you are running it. So if you are running it on the GPUs, then you can configure it with MUG'2 GDR, and if you want to run it on CPU, then you can use the MUG'2X library. So MUG'2X provides a better performance than MUG'2, as it has several advanced features like XPMEM, ODP, and DC support. So now let's talk about the different kind of parallelism we can explore in CPU-based training. So in today's morning keynote talk, Brian talked about the data parallelism and other types of parallelism also. So that's why, building upon that talk, in this talk I'm going to talk about the model parallelism. Why do we need model parallelism? So basically, in the data parallelism, the requirement for the data parallelism is that the model has to fit inside the memory. And we are seeing some out of core models also. So basically, we all know that as we increase the number of layers, we also increase the accuracy of the model. However, we also increase the memory requirement. And the memory requirement can also be increased because of the increase in the input size. So to give you an example, so basically in this graph, we are showing that the memory requirement with respect to the input image size. So as you can, so basically most of us have trained the models on ImageNet or Cypher dataset, which has like 32 or 224 image size, pixel size. However, in the application areas like the medical pathology, we have like 50,000 pixels in one image. And not in the real world also, like if you click a picture from your iPhone or your Android device, you can have a big image size as big as the 3,000 pixels. So definitely we need model parallelism. As you can see that when the image size is 700, like most of the architectures cannot train your model. So that's why we need model parallelism so that we can train the out of code models. Model parallelism sounds interesting, but it is not easy as the data parallelism. As we have to, in the model parallelism, you have to partition your model, and you have to also work on scaling the model to the larger number of machines. So there are several challenges in designing a model parallelism system. So that's why we propose design and implement the Hyperflow deep learning framework, which is very easy to use and gives the high performance using the MPI libraries like MUG'20. So it is based on the Keras models and exploits the TensorFlow 2.x either execution. So basically in the TensorFlow, you can give your model in the form of the Keras definition library like this. Then Hyperflow will automatically partition your model. So in this case, it is partitioning the model into 3 partitions: partition 0, partition 1, and partition 2. So and it will also insert the communication primitives between those partitions so that we can realize the forward and the backward pass. So model parallelism alone is not enough, because as you go to the more number of nodes, it will not give you the as good speed up as the data parallelism. So that's why we have combined the model parallelism with data parallelism, and it is called the hybrid parallelism. So that you can scale your model to the large number of nodes also. So let's go over the results. So here we are presenting the result for the ResNet 1K model on 1 node and 2 nodes. So basically here the result is on the single node, and here is the result for the 2 nodes. So as you can see that even on the single node, using the hybrid parallelism or the model parallelism, we are able to beat the data parallelism and sequential training. And on the 2 nodes, we are continuously beating the data parallelism. So the reason for this type of speed up is because when it comes to the CPU, we don't have a very good implementation for the deep learning framework. So that's why we are seeing such a good speed up, and we can actually, so as the model parallelism have pipeline mechanism also to parallelize the things. So that's why we are seeing the very good speed up using the Hyperflow deep learning framework. So now let's move to the higher number of nodes. So we ran our experiment at 512 nodes on the tech Frontera. So basically we are running model parallelism on the single node, and then we are creating the 512 model replica. So we will do the data parallelism on 512 nodes. So the total course is, as you can see, that it is roughly equal to the 25,000. And to scale our model better, we are using the MUG'20 library. And we are getting a pretty good speed up on 512 nodes. As you can see that we are getting around 481x on 512 nodes and 253x on 256 nodes. So it is very, very close to the linear speed up. So this paper was presented in the ISC 2020. So to conclude my talk, in this talk, we talked about the data and model parallelism, data model and hybrid parallelism, and we discussed about the need for the hybrid parallelism. And that's why we proposed and designed the Hyperflow system, which gives which provides an easy to use interface to the users. And we also did the performance evaluation on large systems like Frontera and achieved a very good scaling efficiency using MUG'20. So thank you very much. Now I will be happy to take the questions. Are there any questions?
Thanks, Arpan. Any questions? One quick question from me. You showed the TensorFlow numbers. Can the framework be used for other, like a PyTorch, MXNet, other kind of things? Or
so our current implementation is only for the TensorFlow, but we are working for the PyTorch and the MXNet. So in future, we will have the implementation for PyTorch and MXNet deep learning framework.
Of course, currently you showed only homogeneous CPUs. Can this work with the heterogeneous CPUs, like if we have mixed architectures?
Yes, Dr. Panda. It can work on heterogeneous CPUs also, because it is only on the logical level we are doing the model parallelism. So yeah, if we have the heterogeneous system, then it will be very interesting to see how. So we will also have a load balancing module in our framework, so that we can balance the load between the heterogeneous nodes. So it will be an interesting thing. It will be an interesting experiment to run on the heterogeneous nodes.
There is one. There are a few more questions. Can you take a look at the Q&A box?
Yes, sure, Dr. 1 second. Let me convert my pointer to arrow. Might be you will be able to compare per watt uses for CPUs and GPUs. Okay, so I'm not very sure what is the question here, like per.
No, the question is, I mean, as we know, the GPUs consume more power. So I think the person is asking if you are getting this performance, so how much DL performance per watt?
Oh, per watt. Okay. So
watt.
Yeah, it will be an interesting experiment to run. I haven't ran it, but I think we can run this type of experiment to see that what is the per watt performance for CPUs and GPUs. I haven't run any experiment till now, so I can't comment on it. So the next question is, if poor CPU implementation improve, will the speed up still near linear? Yes. So we are comparing the performance with the one node, with the improved optimized performance on the one node. So we are seeing good speed up with respect to our optimized implementation. So we are getting good speed up for that implementation also. Okay. We are not comparing with the poor implementation. Yeah. Okay, thank you.
If there are no other questions, then let's thank Arpan also. So this concludes the today's program. But let me quickly give a preview of tomorrow.